Okay, this leads to our first binary linear classifier in the more general framework from the previous Bayes classifier we discussed. And we're going to discuss something called the perceptron algorithm. Okay, so the perceptron algorithm is one where we're going to assume that things are easy. So let's assume that we have a data set that's linearly separable. So one that looks like this, where we have vectors xi, where we assume that we have two-dimensional inputs. We attach a 1 to create a third dimension. And the original data in R2 is linearly separable. So the blue class and the red class are two classes. And we can draw a line separating those two classes. We know what we know that means that we can find a vector w such that the sign of xi transpose w equals the corresponding label yi. In this case, our classes are linearly separable, and so we can find the line that will separate them. In fact, we can find an infinite number of possible lines. The perceptron algorithm, which was developed in 1958, is a first go at binary linear classification. It's going to assume that the classes are linearly separable, which is not a good thing. But it makes that assumption, and it uses a linear classifier of this form, where we predict the label of x to be equal to the sign of the dot product between x and w, where I've done the trick again of assuming that we have a dimension equal to 1 for x to account for the offset. Okay, so the perceptron is one way of learning a linear classifier of this form, where we predict the label to be the sign of the dot product between our covariate vector x and coefficient vector w, where again I've assumed that the vector x has a dimension equal to 1 to account for the offset. And the perceptron is defined by this objective function. And we're trying to minimize this thing. It's a function of the data and of the vector w. We're trying to minimize it in w. So to see why we would want to minimize this thing, let's look at what this term is equal to. We've already discussed how the dot product between x and w is going to be equal to a positive number if x is on the positive half of the plane defined by w, and it's going to be a negative number if on the negative side. Y is the corresponding label for x, and so this value is going to be positive if we predict correctly. If we predict the label yi correctly, this dot product will be equal to a number that has the same sign as yi. And so their product, whether they're both negative or they're both positive, their product is going to be a positive number. If we get yi wrong, if for our particular vector w we predict xi wrong, then the sign of this dot product is not going to equal the sign of yi. And so the product is going to be a negative number. One of them will be positive, and one of them will be negative. And here now, what we're doing is we're summing up a number times an indicator of getting it wrong. So really what we're doing is summing up this value over all points that we predict incorrectly according to some vector w. And all of those points are going to be negative. And so the sum of those incorrectly classified points will be negative. We put a negative sign out front to make it positive, and now we want to minimize that. So we want to minimize this number of points that we get wrong in this sense. So now how can we learn the perceptron? We have the objective function that we're going to try to minimize. The next problem is to try to learn the vector w that minimizes that objective function. Unlike previous techniques that we've discussed, we can't find a minimum by simply taking the derivative with respect to w and setting it to 0. So we can take the derivative of the objective, but then when we try to find a solve for w such that that derivative equals 0, we quickly find that there's no analytical solution. So we need some sort of an iterative algorithm. even though we can't solve this derivative, the root of this derivative analytically, the derivative does tell us something about the objective. What it tells us is the direction in which w is increasing. So the derivative of the objective function with respect to w evaluated at a particular point w says move in this direction if you want to increase the objective function. Therefore, if we pick a sufficiently small eta, what we can say is that if we update the vector w by moving in the opposite direction of the derivative, scaled by some tiny value eta, we will get a new value for the vector w such that our objective function at that new value is less than the objective function at the old value. And this is a general method for optimizing objective functions called gradient descent. And we're going to see an example of this for the perceptron where they do this in a stochastic way. First, I'm going to discuss the algorithm for learning the perceptron. As an input, we have training data where we have labeled pairs, the covariate x and its label positive or negative 1 for y. And we have a positive step size eta. The first thing we do is we initialize the vector w to a vector of all zeros. And then for each step in our algorithm, we want to update the vector w. The way that the perceptron does this is, first, it searches for all examples in our data set that we get wrong according to our current vector w. So find all of the data in our training set that we predict incorrectly given the current vector w. If one exists, pick one at random, and then update w by taking a step in the direction of the label times the vector x scaled by eta. Otherwise, if we can't find anything we get wrong, we've found a hyperplane that separates our data, and so return the vector w as the solution because it can classify our training data set perfectly. So the question is, what is this doing? Here's our original objective function that we're trying to minimize. If we took the gradient of this with respect to w, and we define the set mt at iteration t to be the set of misclassified training observations, then the gradient would be equal to this. So I'm taking the gradient of this with respect to w. I'm only summing over the points that I get wrong. And we find out that the gradient is equal to this. If we did full gradient descent, what we would do is we would update the vector w to be the old value minus eta times the gradient of the objective evaluated at wt, because we want to minimize, so we have a minus. In that case, we can simply plug in this value here for the gradient and quickly find that what stochastic optimization is doing, which is what the perceptron is using, is just randomly picking one of these values instead of summing over all of them. But in practice, we could have also summed over all of the values and constructed the entire gradient and plugged this in here, and our algorithm would be just as correct. Let's look at a simple example of this, of learning the perceptron for a binary classification problem where the data comes from R2. Again, here are our data points. They're in R2. The x's are in R2, and the labels are color-coded. So red is +1, blue is a -1 class. And we're going to just let eta be equal to 1. Our step size is equal to 1 in this picture. So for the first iteration, let's assume that this is what we start out with. Our vector w points in that direction. That's our classifier, meaning that we're going to declare everything on this half to be positive 1 and everything on this half to be negative 1, meaning that we get anything blue on this side wrong and we get anything red on this side wrong. The perceptron will first pick a misclassified example at random. In this example, it picks this vector, randomly picks this point because it's misclassified as being a blue class. It then updates the coefficient vector W by adding eta times the class value times the vector. In this case, because the class is positive 1, we're adding this vector times plus 1. Okay, so when we pick this as our misclassified example and we update W, we're essentially adding this vector to the end of our classifier vector, and we get this update. So this is our updated classifier after our first step. We then want to pick another misclassified example. In this case, all of these red points are misclassified and all of these blue points are, and this blue point is misclassified as well as this one. So we pick a misclassified example at random. For example, maybe we pick this misclassified point. We then update our regression, our classifier vector W by taking the old value plus the data points that we misclassified and get a new classifier, and then we've converged. So we're done. We've now classified everything correctly. So we've gone through an example of the perceptron in action. There are a few drawbacks of the perceptron that make it not used so much anymore, even though it's a good first algorithm to learn. In future lectures, we're going to discuss other algorithms that fix the problem that the perceptron encountered. One drawback of the perceptron is that if the data is linearly separable, there are an infinite number of hyperplanes that can separate the data. But the perceptron is only going to return the first one it finds. Once it finds a hyperplane to separate the data, according to the algorithm we've discussed, there are no more changes that can be made because there are no more misclassified examples. And so it's going to return the first hyperplane that it finds. However, not all hyperplanes are equal. Some may be better than others. For example, we might want to define the hyperplane so that the nearest point to the hyperplane is as far away as possible. In this example, for example, this blue line separates these two classes as well as this one. However, this blue line is extremely close to this green point. Maybe we want to find a hyperplane that separates the data but is also far away from any of the data points. The perceptron is not going to do that. Also important is when the data is not linearly separable, which is usually the case, this perceptron algorithm is not going to converge. So it's just going to continue to keep picking misclassified examples and updating the hyperplane, but it's never going to converge. And so it's important to define an algorithm that will actually converge in a finite amount of time, and this is also what we're going to discuss in future lectures.